Okay, so as I said in this presentation, I will talk about Wasserstein barycenters and more generally about barycenters for transport costs. So the talk is meant as a quick, short overview about the subject, and at the end, eventually, I will speak about work in progress, something new that we did with my colleague Nathalie Gaussians and Éloi Tanguy. Okay, so just to give a bit of context, as you all know, we have in all part of society, we have an exponential growth of data, and we need ways to represent this data in a more compact way. So we need to compute representation of this data, which is more compact. So we need some kind of notion of an average representative of data. And this data can be high dimensional, it can be complex. It can be points in a high dimensional space. It can be distributions, probability measures. So you have to be able to compare these probability measures, these distributions, this data. And, or you might want to compute clusters to group this data into current clusters. So which means clustering means averaging also, because for each cluster you have to compute representative mean. So you need some kind of notion of barycenters to analyze all of this available data. So let's go back to the notion of barycenters that we learned at school. So what we learned is that if we have p points, x1, xp, of a generic space X, and if I have weights summing to 1 and non-negative weights, then a good representative of these points, of this set of points, might be the weighted means. So that's the notion of barycenters that we learn at school. And of course, in an Euclidean space, if you have points, it might be a very good idea, a good representative. But if you have other kind of data, or data in, for instance, function or probability measures in a L2 space, and if you compute this weighted mean, it does not make sense for all applications. It might be strange to compute this means here. So what can we do about this? So first, let's define barycenters in a more generic way. So I assume that I have cost functions on my, so Ci is a function from the product space X cross X to R plus. And I can always define this problem, this optimization problem, one where I'm looking for the minimum, I'm looking for the minimum of the weighted sum of the cost between X, which is what I'm looking for, and the Xi. So if I define barycenters like this, the barycenters of the Xi for the weight lambda I, if I'm in a Euclidean space and I take the square norm for the Ci, then I find the weighted mean. So it's my classical notion of barycenter learned at school. But if I take for the Ci, I take only the norm, not to the square, then I find something else, which is a weighted geometric median. And of course, it's much robust to outliers, for instance, that's the weighted mean. So you might want to use this for some applications instead of the weighted mean. And of course, well, the bad thing is that you don't have any, there is an algorithm, but there is no explicit formula to compute this geometric median. And of course, you might want to use something else, a norm to the power p, or even a cost which is not derived from a norm. Okay? So how can I use this? How can I extend this to define barycenters between more complex notions like probability measures, for instance. So for this, I will need optimal transport. So just a reminder, even if I suppose that most of you know everything about optimal transport. So I suppose that I'm in a space, X, and I have a cost function on X, which tells you, so C of xy tells you how much you have to spend to go from X to Y. And I want to define a cost, not between points, but from this cost between points, I want to derive a cost between measures, probability measures on the space. So I take two measures, mu0 and mu1, and I will need the notion of couplings between measures. So a coupling between two measures, between mu0 and mu1, is only a probability measure on the product space with marginals mu0 and mu1, okay? So it's also probability measures, but on the larger space with marginal mu0 and mu1. And the optimal transport cost or Kantorovich cost between mu0 and mu1 for the ground cost C is defined as the value of this optimization problem. So it's just a linear problem on gamma, and you take the gamma, which minimize this linear quantity among all couplings between mu0 and mu1, okay? And under some some good hypothesis, you can show that this gamma, this optimal coupling, is supported by a graph of a function, and this function is called an optimal map between mu0 and mu1. Okay, so if you look at the literature, so there is one very good property, an interesting property for us of this Wasserstein cost, is that if your ground cost is a distance to upper p with p larger than 1, then you know that your cost is actually a distance between probability measure, and those distances are called Wasserstein distances. Okay. And those distances also have the good property that they metrize the weak convergence of probability measures. So that's really nice to have. Okay, so let's go back to our barycenters problem. I assume that I have mu1, mu_p, which are probability measures, and I still have weights summing to 1. And so the colored points are my measures, one color per measure, so I have 4 measures here. And I want to define barycenter for this transport costs. So I have C1, Cp, which are costs, ground cost on my space, and I can always try to find a solution to this optimization problem. Is there a pointer? This one?
Yeah, this is in principle working.
No? This one? No. Well. No, it's okay. I can do it. Je peux m'en passer en fait. Okay, it's not a big deal. Ah, yes. Ah, great. Thank you. Okay. Of course, Mathieu didn't need one. Okay, so I just took the notion of barycenter we had before with the cost C1, the ground cost C1, Cp, and I lift it to the probability measure space, and I have this new notion of barycenter, which when you take the cost here, when these costs are Wasserstein distances, then you will call this a Wasserstein barycenter. Okay, so it's not, you can show that under very mild condition on the costs here, this barycenter is well defined, but of course it's not necessarily unique. So if we look at the literature on the theory of Wasserstein barycenters or barycenters for transport costs, then to the best of my knowledge, this is the first paper addressing this problem, and it's a very generic. Well, they consider the problem with very generic ground costs. They just have to be continuous, I think. But this paper is less well known than this one. So this one is called Matching for Teams. And it's less known than this one, which is considered as maybe the foundational paper on Wasserstein barycenters. But most of the theory is already there. But in this one, which is really, both papers are, of course, very nice. But in this one, they focus on the Wasserstein 2 distance, and they show existence of barycenters. They show uniqueness if the measures are absolutely continuous. And they study the special case of Gaussian, and they show stability and a lot of things. Okay. So more recently, we have several works extending the results of these two papers to other Wasserstein distances. So for instance, the Wasserstein medians again by Carly and colleagues. And also other works for WP or for WH for specific H. Okay. Okay, so what can we do if we want? So I said a few words about the theory, but what can we do if we want to compute Wasserstein barycenters? Well, there are two cases where you have explicit solutions. The first case is not on the slide. The first case is the 1D case. So numerics. So you have explicit solution in the 1D case if your cost is a function h of x minus y with h convex. In this case, you know that you know how to compute explicitly the barycenter, and it's just monotone reordering rearrangement of the measures, so it's quite easy. But if your ground cost is not like this, so it's not true anymore, so you don't have any explicit solution. And the second case where we know how to compute an explicit solution is the case of Gaussians in any dimension, but it's true, you have an explicit solution only for W2. Okay, and the explicit solution for Gaussian is given here. So you assume, yes, it's working. Okay, you assume that all your measures are Gaussian with mean mi and covariance matrices sigma I. And then you can show, so again, it's shown in Carlier, you can show that you have a Gaussian barycenter, and the mean of this Gaussian is the weighted mean of the means, so it's very intuitive and nice. And the covariance matrix is itself solution, is a barycenter of all the covariance matrices of your Gaussians, but it's a barycenter for something which is called the Bure distance between covariance matrices, and which is defined like this. So you will, in this kind of papers, you will, in applied papers, you will often see representation, illustration like this, where each Gaussian is represented by an ellipse. And so you take the 4 Gaussians represented by the 4 corner ellipses here, and you compute all possible barycenters between them. Okay. So what can we do to compute transport costs if we are not in these 2 cases? Well, first there is bad news. The bad news is that it's an NP-hard problem. So what does it mean? It means that, of course, we have polynomial time algorithms to compute barycenters, but the dependence of the cost of this algorithm is, so if you fix the dimension of your space, or your, then it will be polynomial, but the dependence in the dimension of the space is exponential, or depending on the algorithm, it can be also exponential. It might be not exponential in D, but in this case, it will be exponential in the number of marginals that you have. So if you have 2 marginals, it's okay. It's 3, it's okay. But if you have maybe 10 measures and you want to compute the barycenters, and each measure has n points, then it means n to the power 10. So at some points, you cannot use this anymore. So still, some algorithms. So the most, well, the one algorithm coming from linear programming is quite easy to implement if you have some linear programming library, is to use the fact that the barycenter problem is equivalent to a multi-marginal optimal transport problem. So that's the algorithm with the exponential dependence on the number of marginals. So again, if you have 10 marginals, you don't want to use this, okay? 10 or more. So to the best of my knowledge, one of the first papers proposing an efficient way to compute Wasserstein barycenters, and actually it's not Wasserstein barycenters, but sliced Wasserstein barycenters. Those are 2 papers by Rabe and colleague. But again, it's not really Wasserstein, it's sliced Wasserstein. And if you want to do Wasserstein barycenters, when you can rely on entropic regularization, that's one possibility, at the cost of adding some smoothness in your results. So the idea is that you replace Wasserstein, you add to your Wasserstein cost a small regularization called entropic regularization, and it makes your problem more convex. And then you can compute solutions by a dedicated Sinkhorn algorithm. So again, it's a very nice solution. And a last possibility, and I will speak more about it in the next slide, is called the free support algorithm. So, and it was introduced, well, it was introduced in the context of optimal transport by Couturier and Doucet, but actually the idea behind this free support algorithm was well known in other fields. So what is the idea exactly? So I have measures, mu0, mu p, and I have weights again, and the idea is to see the Wasserstein barycenter problem as a fixed point problem. Okay. How much time do I have left? 10 minutes, okay. So I want to write a fixed point algorithm, so I will write it like this. And I want to find a good functional G. So G will be a functional between the space of probability measure to the space of probability measure. Okay, it's not a function on the ground space. It's a function on the space of probability measures. And I want to find an appropriate G. So this algorithm converges to Wasserstein barycenters. So how can we do this? Well, the idea is summarized in this drawing and in this definition here. So the idea is, so let's start with a drawing. So those are my measures, and I want to compute the barycenters of these measures. So I suppose that I have a first estimation of my barycenter, which is called rho. And I just compute the optimal maps for optimal transport between rho and this mu I. So I suppose that this map exists for the moment. And I will take the weighted average of this map, and then I will compute the push forward of rho by this weighted average. So it means that if you have a random variable following rho here, and if you take your tk as the optimal maps between rho and uk, you just compute this new random variable, which is the weighted mean of the images of x by the tj, and then you take the law of this new random variable, and this is your functional g. Okay, so it's quite natural to compute it like this. Okay, so from rho you go to the g of rho, and then you start again. Okay, from g of rho you compute again the optimal maps to the mu k, and you compute this, and you iterate. And there is a very nice paper by Alvarez, Esteban, and all, and colleagues, which shows, so they show that if you take, if you are computing barycenters for W2, and you have absolutely continuous measures, then barycenters will be fixed points for G, which is quite intuitive. And they also show that you have convergence of subsequences of this algorithm to a fixed point. And if the fixed point is unique, then it will be a barycenter. But they heavily rely on the proof. You really need to have optimal maps to write this algorithm like this. And to have optimal maps, you have to make hypotheses. So that's why they need absolutely continuous measures here. Okay, so what can we do if we want to go beyond the Wasserstein distance assumption? So I want to compute barycenters, but maybe not for WP or W2. So sorry. So 3 years ago, we considered the following problem, and we will see why it's also a barycenter problem. We suppose that we have measures, probability measures, but they're not living, all of them are not living on the same space, okay? They're living on smaller spaces, or Euclidean spaces, just to simplify, RDI. And there is a link between of this RDI, which is given by linear application PI, okay? So I have my PI, which goes from RD, which is the ambient space, and from RD to RDI. Okay, so let's look at this example here. I have each of my, so it was my, at the time I was very obsessed with Marvel movies. So each of my 3 measures is represented by a point cloud in a plane, okay, so of the di are dimension 2, but my d here is dimension 3, okay? And the question is, how can I find a measure in R3 which, after being projected by the 3 projection P1, P2, P3 on the 3 planes of the canonical base, which is not too far. I want the projection of the whole measure to be not too far from these 3 measures. Okay, and not too far will be expressed as a barycenter problem. So, of course, this is motivated by applications, for instance, in tomography, where you know measures on sliced, on different slices, and you want to reconstruct a measure on the whole space. Okay, so we wrote the problem like this. You have your measures mu I, and you're looking for gamma, which is a measure under the whole space, but you don't want gamma to be close to mu I, but you want the push forward or the projection of gamma by the pi to be close to the mu I. Okay, so in a way, it's a barycenter problem with a cost which is not W2, but the cost includes the pi. Okay? But still, you cannot use the previous algorithms directly to solve this problem. So what you can do is you can go back to the... When you have a transport problem, always start by thinking about solution for direct measures. Okay? So I just take each measure is a direct. So I have 3 projections here. And I'm just looking for, so if I translate the previous problem for directs, it means that I'm just looking for x, which minimizes this. Okay? And of course, there is an explicit solution for this problem, assuming, I'm looking for a point with projections which are not too far from these 3 blue points. And of course, when you derive this and you compute the solution, so you have to make the hypothesis that this matrix here is full rank, is invertible, then the solution is given by this, okay? So it's just the same computation that for the classical weighted mean, but just with pi. And if this is not full rank, then there is some directions when you do whatever you want, and in other directions, you will still have these solutions. So how can we extend this to our generalized barycenter problem? And what we were able to show is that if gamma star will be a solution of the generalized barycenter problem, if and only if the push forward of gamma star by the square root of A is a barycenter, a W2 barycenter of these measures here. So these measures are only the measure mu I that you will project. So those measures of mu I are in R2 in my previous example, but you embed them again in R3, and then you take the push forward with this A minus square root of A, and you compute the barycenter. So basically, if those are my 2 measures, I take the image of these 2 measures by this matrix, okay? And then I compute the barycenter of these 2, and then I go back to my original problem by taking the image of this result by this, okay? So it's very easy. You can take your favorite algorithm to compute barycenters. It's very easy. You can do anthropic, you can do free support, and it works. And it gives results like this. It's very fun. And of course, you can do theory, you can show existence, you can study the Gaussian case with W2, everything remains Gaussian. You can link with multi-marginal optimal transport, you can show many things. And this is for the Marvel logos. And this is included in the Python optimal transport library of Rémi, developed by Rémi Flamaril. So Eloi, which is my PhD student, included everything inside. Okay, so maybe 2 minutes, yes, and this is the last slide. So it's perfect. So what can we do So we had this problem with this generalized barycenter definition. And this year, we met someone called Christophe Gaillac, who he's a researcher in economy at the University of Geneva. And Christophe told us, okay, I use your algorithm. It's very useful for some economic problem, but I need to solve the same problem, but I want the PI to be nonlinear. So I want to solve this. I want to find solution of this. And of course, if the PI are not, so Fi are not linear, and of course, if this function are not linear, everything that we did doesn't work anymore. So we started thinking about this and how we could compute solutions. Of course, it's easier to think about it very generically and to think about how you can find solutions of this problem, because your Fi, you're pushed forward by Fi, you can put it in the cost, okay? So your cost Ci would be something like this. For instance. Okay, so at the end, we started wondering if the fixed point algorithm proposed by Couturier and Doucet, and also studied by Alvarez, Esteban, and colleagues, if it could work, if this algorithm could work again for very generic ground cost. And what we found is that it works under very mild assumption. And the main assumption is that this function, this barycenter function, has to be unique because you need some sort of continuity. Okay, so if your costs are continuous and if you have a unique solution for this, then you will have continuity of your barycenter function in function of the data. And if you have continuity, then you can work. You can simply define G as the law. So this time is X is following a row, the low row and distribution row. And if you take, again, for simplification, I assume that I have a transport map between rho and mu k. So I don't take the weighted mean anymore, but I take the barycenters. So the solution, this unique solution of this problem between the Ti of X, the image of X by the Ti, and then I can show that barycenters are fixed point of G, and I can show convergence, some kind of convergence. And the good thing is that it also works if you don't have optimal maps. So it also works with transport plan. And I won't go into details, but this is a first example of this algorithm with W1 instead of W2. Okay, and I will stop here because I'm running out of time.